One of the things that were confusing to me when I started learning how to program was actually the data-oriented design. And the first question that I had in mind was, why do we even need it? And when actually do I want to use it? Because when I started, I was actually trying to over-optimize everything that I could. And in reality, I just wasted time. It was good to learn new things, though, how to do it, when to do it. But it was bad in a way that I wasted a lot of time on things that didn't really matter. So when do we want to actually use it? We want to use it when we do something where execution speed is really crucial, such as game engines, real-time simulations, or high-frequency trading systems. The list can go on, but I guess you get the idea. Also the large-scale data processing, or just multi-core parallel systems that need to process a lot of things. And why exactly do we want to use it in that? Well, pretty much we can improve the cache efficiency, so pretty much the hardware will love us. We can enhance the CPU utilization, so we can get more out of it. And we can increase the scalability and performance, plus reduce the overhead. So pretty much we can reduce the amount of instructions that we do. And this is how we do it. A simple example could be structure of arrays versus arrays of structures. So in typical small applications that you might be doing, it might not even matter. But once we scale to something bigger, there are actually differences that we need to take into account. For example, structure of arrays allows us to organize our data in separate arrays per attribute or per certain data that we need to do something with. And it can be really helpful when we can avoid actually using certain interfaces or just, well, vtable invocations and use something that has very similar data so that cache coherency will be with us. And also we will get way less cache misses. Whereas for the array of structures, we can get this typical object-oriented layout where we get one big thing of a chunk, and it contains a lot of things that may lead to a very poor cache utilization. So here's an example. Let's say that we have an array of objects and it has like a very base type object inside of it. And pretty much when we call something on the object, we call some interface call, which is just a virtual method. So it invokes some virtual table call, whereas for the explicit arrays, I can divide those objects into lights, meshes, visual effects. Of course, I can keep on dividing those, but, well, we need to find some common ground where enough is enough. And here, for example, I divided it into 3 different loops, where one is calculating lighting, the other one physics, and the third one some effects. And, well, now, when I run those loops are actually calculating things that are local to this certain object. So, for example, only to this light. And later we can maybe divide it into light types, mesh types, visual effects types. Well, we can actually, and it can increase performance, depending, of course, on what exactly would be in those updates. But if there's similar global data or anything related to that, we can get a lot from the cache. Not to mention just that we know what's the next object and what do we want to exactly to call. So here's a performance example from direct calling something and indirectly calling something via the virtual table, pretty much just the virtual methods. Here you can see that we have the lee-rcx object, which is pretty much loading the address of a certain object, and then we are doing the call of the update. And because we are doing a direct calling, there's no polymorphism involved. We already know at the compile time which method we want to call, and pretty much it sums up to 2 or 3 cycles. Of course, it depends on the CPU, but there's just some approximation. Then we've got the indirect calling, and here we can see that first we need to load the vtable pointer, and it's a memory access. And again, memory access, we need to load the function pointer from the vtable, and only then we can call the certain function, which also costs more and can potentially even cause a misprediction because, well, we don't know at the compile time which method exactly will be called at this certain moment. And because of that, the CPU will try to predict that. And if the prediction fails, we can lose 10 to 20 cycles, again, depending on the CPU, but I guess you get the idea. And when we sum the cycles, even in the best case, the vtable is, well, 3 to 5 times slower, right? So we can see something that when we scale the amount of data that we need to process, it can lead up to some bigger amount of cycles for just a very small thing. And the next thing would be the cache efficiency. Here, a pretty simple example, we just want to use a contiguous memory, so pretty much allocate an array that has one big blob of allocated memory without gaps, and then use it, reuse it, and use it in a linear manner where we go from a certain point to another point without any gaps or jumps, but just linearly going from start to finish. Then we want to avoid the pointer chasing, which is pretty much avoiding random pointers to certain places in memory if we can, and linked structures that also just point us somewhere to the memory, but we don't exactly know where sometimes. So yeah, this. The next thing is to reduce or eliminate branching. And the thing is, having an if statement that happen very rarely, for example, something can happen maybe once every like few hours or something like this, it shouldn't really matter. Of course, it depends, but we shouldn't really care about it. And well, it can stay, but if this is something that happens very often, then the branch predictions of our hardware cannot really help us, and well, the branch can be costly. So to avoid that, we can think of ways to utilize our data approach of making things explicit for certain objects or just certain data, and just try to avoid branches this way. And the last thing is multithreading. And multithreading, it comes to a way that we want to divide our data so that there is no collision between the threads, or minimize the collision as much as possible. We want to make it so our data is organized to a very minimal shared state, so that every single core can compute its own like chunk of data that it can. Therefore, we can have our own structures be optimized for like bigger systems or bigger utilization of the hardware. And well, from the very basics and well, the overall understanding as I see it, that would be it. Thank you for watching and cheers.